Hey, y'all, let's do some of these radioactive decay problems. How do we solve these half-life problems? Real quick, what are half-life problems? Well, let me do a thought experiment. Let's say my teaching is so bad that every 5 minutes, half the class just gets up and walks out. Well, if I know that rate of leaving my classroom, I can do some predictions and some calculations. So, 32 students are my initial time, and then 5 minutes after that, I'm down to 16 kids. And 5 minutes after that, I'm down to 8 kids. 5 minutes after that, I'm down to 4 kids. So it lets me predict either how many kids will be left after like 20 minutes, or if there's only like 2 kids in my classroom, how long has class been going on for? Either way, that's the concept behind these half-life problems. But instead of kids leaving a crappy teacher, we do it with radioactive unstable isotopes. How long does it take for them to degrade back down to their more stable state? These radioactive isotopes, and that lets us also talk about how long it takes for radioactive waste to stick around, and that's a big deal. So to do these problems, it's all just about setting it up. So an isotope has a half-life of 6 hours. Boy, that's really radioactive. That's unstable. What percentage will be left after 24 hours? So all I had to do is just set it up. I always do Microsoft Paint, time at the top, then half-lives, and then in this case it's telling me percentage. Sometimes that will be the number of grams left or the amount of radioactivity. The top two rows are always going to be the same. The bottom one depends on the question. So students love to screw up this part. They love to skip the 0 here and the 0 here. After 0 time, 0 half-lives have happened. Then I just say 1, 2, 3 half-lives, 4 half-lives, maybe 5 half-lives. Um, Initially, I'm starting off with 100%. So after 1 half-life, 6 hours, 6 plus 6 is 12, 12 plus 6 is 18 hours, 24 hours, 30 hours. Oh, doesn't matter. I can tell right now my answer is going to be here somewhere. So half of 100% is 50%, half of 50% is 25%, half of that is 12 and a half of that is 6.25%. So that's my answer for this question. Easy. All you have to do is just set up the table. Don't forget to zero it out at the initial moment, and you can do those. Let's do one more, just for funsies. So, no, not there. Oh, The Shins, that is a good album. You might want to give that one a go. Let's do this one. Carbon-14 has a half-life around 6,000 years. It's 5,700. Okay, the initial rate. Oh, this time what I'm doing is I'm doing radioactivity. I'm doing initial activity. I'm not doing percentage or grams. Okay, so again, what do? I set it up, time, half-lives, and in this case, it's counts per minute. Counts per minute. Cool. 0 time has happened, 0 half-lives. 1, 2, 3, 4, 5. I hope it doesn't go more than that. And I start off with 200 counts per minute. 6,000 years, 12K years, 12,000, 18,000, 18 plus another 6 is 24,000, plus another 6 is 30,000. I hope I don't need more than that. So now let's half each time. Half of 200 is 100, half of that is 50, half of that is 25, half of that is 12 and a half, 12.5, oops, half of that is 6.25. What's my question? Fall below 10 counts. Below 10 counts will be right here somewhere. So how long will it take? Well, it's in between here somewhere, so it's going to be 30,000 years. It's not asking me for half-lives, it's asking me for how long. Either way, my answer is there, and specifically my answer is this top row, 30,000 years. So that's how we do these half-life problems. Set up the table, and you can figure it out. In real life, the scientists they'll figure out, okay, wait a minute, let me science it, and if I have 6 beats per minute, counts per minute, this spear fossil must be 30,000 years old. So actual scientists really do this in real life. We talk about this in apes to talk about how long it takes for radioactive waste to be safe, thousands and thousands of years. I hope this was helpful, and I'll see you guys later. Bye. Boop.